In this second video here, we're going to pick back up with the hydride ion. We learned that the hydride ion has 2 electrons and only 1 proton in this particular isotope of hydrogen. Now, the 2 negatives are offset, or the 1 negative offsets one of the protons. So these 2 offset each other. 1 positive is offset by 1 negative, but this negative here has no proton to balance it out. So this is a negative ion. Why would hydrogen want to get another electron and become a 1 minus ion? Because an element that has 2 electrons is helium. And helium is chemically stable. Helium is inert. So for some reason, having 2 electrons makes you stable. Let's see why. Let's try to add a 3rd electron here. Look and see where it goes. I'm trying to add a 3rd electron to hydrogen's first level. Here's the first level, or the first orbit is right here. I'm trying to add an electron to it. It will not hold it. It goes out to the 2nd energy level, or 2nd orbit. When you have 2 electrons on that level closest to the nucleus, that level is full. It doesn't hold anymore, and that is what makes it stable. 2 electrons on that level, a filled level like that close to the nucleus is stable. Let's take a look at the questions that go along with this. We've already looked here about how to figure out the mass number and the net charge. The hydride ion has the same number of electrons as helium. Helium's atomic number 2, so it starts with 2 protons. That means it needs 2 negative electrons to balance out the 2 positive protons. Why does it make sense for hydrogen to want to do that? Become 1 minus. Or in this case, I just have a minus sign. It's trying to get chemically stable like helium. Helium is chemically stable. What does this have to do with the duet rule in question E? Well, the duet rule says, the octet duet rule says that stability comes in 8s or 2s. That first level closest to the nucleus, called the first energy level, we saw only holds 2 electrons. So when that thing can be left full, it is stable. The duet rule applies to the smaller atoms only. So the reason you'll often hear the octet rule without the duet part being attached has to do with the fact that the duet rule only applies to a few atoms. So here's hydrogen. I'm going to add another, wrong spot. I'm going to add another proton to the nucleus. I have helium. That's satisfied by the duet rule. I'm going to add a 3rd proton, and now I have lithium. Or a 3rd proton, I now have lithium. I need some neutrons in there to keep these things. I'd like to keep that nucleus somewhat stable. There we go. So now I have 3 protons in there. I have lithium, but it's a positive ion. So I need to add 1 more electron to it. There's the neutral atom of lithium. Lithium is not chemically stable. How many electrons would lithium need to lose in order to be left stable? Well, if lithium loses this 1 electron right here and becomes a positive ion, if another element can rip that electron off, it has satisfied the duet rule. I now have a positive ion. It's a 1 plus ion. Interestingly enough, take a look at what our periodic table of ions says regarding lithium. Lithium is right here. It's a plus, has a plus there, which means it wants to be 1 plus. Now we understand why lithium wants to be 1 plus. Lithium wants to be 1 plus because if it's 1 plus, it's left with 2 in its outermost level. Its first energy level will have 2 in it, and that is stable. What about the next one over, beryllium? I add another proton to the nucleus. I now have 4 protons. I need to throw a neutron in there to balance it. There we go, a couple neutrons in there to balance it, to keep those protons apart. It's a positive ion, so I need 1 more electron in there, and now I have 4 total electrons to balance the 4 protons. But is beryllium chemically stable? What will beryllium try to do? It's going to want to satisfy the duet rule. So it's going to want to lose that electron in a chemical reaction, and if it can, it would like to lose that electron in there, and that makes it 2 plus. It now has 2 protons that are not balanced by 2 electrons, and it's satisfied what we would call the duet rule portion of the octet duet rule. So if beryllium loses those 2 from its second level out, it would be left stable chemically like helium. Let's take a look and see if that makes sense according to what we see on this chart right here. There's beryllium. Now we understand why there's a 2+ after beryllium. If it loses 2, it starts with 4 electrons. If it loses 2, it would have 2 like helium. It would be a noble gas. It would act like a noble gas. It wouldn't be a noble gas. It would act chemically like the noble gas. The only way we could make beryllium a noble gas is if we ripped out 2 protons from the nucleus, leaving it with 2. All right, so there's an explanation of the duet rule, and we will now take a look at doing some of the carbon isotopes in part 3 of the lab. Carbon isotopes, and they're going to want to start off. We learned about 3 carbon isotopes: carbon-12, carbon-13, and carbon-14 in our notes. Carbon-12 has 12 total particles in the nucleus. We need to look at a periodic table to see how many of those are protons. So here's carbon. It has an atomic number of 6. So carbon has 6 protons, and in this particular isotope of carbon, there are 12 total particles in the nucleus. So they want us to build this thing right now. All right, let's build it. Reset this thing. We need 1, 2. Well, 1 is proton or hydrogen. 2 protons is helium. 3 is lithium. 4 is beryllium. 5 should be boron. 5 should be boron. And 6 protons is carbon. So that's carbon with 6 protons, but I need the mass number to be 12 for carbon-12. So I'm going to add 6 neutrons. I'm going to keep adding neutrons till I get it to 12, and that was 6. 6 and 6 is 12. Now, it is a positive ion. Right here, I see that there are 6 protons, so I need to add 6 electrons to balance those out. I'm putting the first 2 there. I'm going to try to put the third there, but we already learned that that first level only holds 2. So that goes to the next level, next level. That's the second level, second energy level. Slang term, you could call it the second orbit, but it's not an orbit. It's really an orbital, three-dimensional patterns, not two-dimensional orbits. So now we have carbon-12's atom. Let's take a look at it. There's the drawing of it. Here you just had to put in 6 protons, 6 neutrons. 6 and 6 is 12 for the mass number. There's 6 protons for the atomic number. We look down here. Was it stable? I forgot to check. Let's go back. Click on stability. Yes, it is stable. It seems like we have enough neutrons to keep the protons far enough apart where they're not going to repel and have the whole nucleus fall apart. How many fit on the inside orbit? It was 2. How many fit on, or how many were left on that next orbit? There was 4 on the second energy level. There was 4. Now it's asking us to take a look at the Roman numeral above carbon's family on the periodic table of ions. We see 4 electrons right here on the second level. We see 4. Now let's take a look at the periodic table of ions. There's carbon, and it says go up to the top. From there, we're going to move up. There's a Roman 4 above it. There's a Roman 4 above it. It's interesting that there's a Roman 4. It's interesting that there's a Roman 4 and that there's 4 in the second level or outermost level, which we call the valence. The level furthest from the nucleus that has electrons on it is called the valence. So the valence of carbon is 4, the Roman numeral of 4. The numbers are the same. And that's what we're going to try to see as we continue on with the lab in other parts. The next one they're asking us to do is carbon-13. Carbon-13 is going to be the same exact number of electrons because carbon starts with 6 protons. We can't change the number of protons and have it still be carbon. But the mass number has gone up to 13, so we're going to have to add an additional neutron to the nucleus. Here we go. There's carbon. If I try to add one more proton, because this is carbon 12, we want carbon 13. If I try to add another proton to it, I now have nitrogen. I've changed the atom. Changing protons changes the atom. I want carbon 13, so it's a neutron that we must add, and it's remained stable. It remains stable. Let's take a look and see what questions they're asking. Yep, mass number went up to 13. 6 and 7 is 6 plus 7 is 13. We couldn't change the number of protons, so the atomic number stayed the same. Atomic number is number of protons, and it is stable. Now we go to the next one. They want us to do the next isotope of carbon. We, again, cannot change the number of protons. We have to keep that 6. To get a total of 14 particles in the nucleus, we have to add a neutron. We don't want to change the number of electrons. That won't do anything to make carbon 14. 14 is the mass number, meaning we need 14 particles in the nucleus. 6 of them are protons, so 6 of them must be neutrons. Let's see what happens here. I need to add another neutron. I now have carbon 14, but the nucleus became unstable. Now the nucleus is unstable again. All right. Now we have too many neutrons. If the balance between protons and neutrons is offset, the nucleus became unstable. The nucleus became unstable for letter D when we increased it to 8. 7 neutrons to 6 protons was okay. 6 neutrons to 6 protons was okay. For the smaller atoms like carbon, you don't want much more than a 1-to-1 ratio. And that's what it says down here in letter E. You don't want much more than a 1-to-1 ratio. As the atoms get bigger, we need more neutrons to mediate or keep the protons from pushing too much on each other. That takes care of part 3 of the lab. Our next video, we will resume and begin discussing part 4.